let's talk about critical numbers, or where something critical is happening in the graph. And remember, when we say where, that's a location. Critical numbers are the x values because we're telling where something critical happens. Let a function f be defined at c. If f prime of c equals 0, or if f is not differentiable at c, then c is a critical number of f. Again, notice f prime of c. This is in place of x. C is an x value. Critical numbers are x values, locations of where something critical is happening. Let's take a look back at the graphs that we talked about earlier. Where are critical things happening? Well, where there's a turning point is something critical. Where there's a hole is something critical. Where there is a sharp point is something critical. Notice at all of these points, either the slope is 0, the function does not exist, sharp point, so the derivative does not exist. So that's why we can find the critical numbers by saying the derivative equals 0 because the slope equals 0 at maximum and minimums, or f is not differentiable at c. F prime of c does not exist. So without having to look at a graph, we can find where something critical is happening, aka the critical numbers, by finding where the derivative is 0 or does not exist. Let's practice doing that without a graph. For numbers 1 and 2, find the critical numbers of the function. So remember, that's where the derivative is 0 or does not exist. So what do we need to do first? That's right, take the derivative. Notice this is a quotient, so as it is, I would have to use the quotient rule. However, I'd prefer not to, and I can split this one up. So that's what I'm going to do first. Let's rewrite this function, 9x squared over x cubed minus 27 over x cubed, which makes 9x to the negative 1 minus 27x to the negative 3. That makes f prime of x equal to, derivative here makes negative 9x to the negative 2, derivative here multiply by negative 3 plus 81 x to the negative 4, and then let's rewrite this, negative 9 over x squared plus 81 over x to the 4th, and then get a common denominator, times x squared times x squared. So we get negative 9x squared plus 81 over x to the 4th. There is our derivative. What do we do with our derivative? So again, remember, critical numbers, that's where f prime equals 0 or does not exist. Let's start with, where does f prime of x equal 0? Here is our derivative. Negative 9x squared plus 81 over x to the 4th equal 0. A quotient will equal 0 when its numerator equals 0. So negative 9x squared plus 81 equals 0, and that's going to happen at two places, at 3 and negative 3. We could factor to see that. Now let's find out where f prime of x does not exist. A quotient does not exist when its denominator equals 0. X to the 4th equals 0, which is when x equals 0. However, looking back at our original function, notice that x cubed in the denominator means that x can't equal 0. 0 is not in the domain of the function. So this is not a critical number because f of 0 doesn't exist to begin with. Let's make a note of that. Not a critical number because f of 0 does not exist. The function has to be defined at the x value for it to be a critical number. However, the function is defined at 3 and negative 3, so these are our two critical numbers for this function. Example number 2, h of x equals the absolute value of x. Before we can do anything with the absolute value function, we should split it up, rewrite it as a piecewise function. What does that look like? Well, we can think of this graph to help us where the vertex is at 0, 0. So this part of the graph is the y equals x graph. This one is the y equals negative x graph, and the vertex is at x equals 0. Or we can think about how we have a positive version, a negative version. The positive version when x is greater than, setting our insides of the absolute value equal to 0, 0, and negative x when x is less than 0. Now, because we have to take the derivative, we'll also include that h of x equals 0 when x equals 0. Why? Because we can't take the derivative at the sharp point. Let's write down what the derivative equals in piecewise form. The derivative of x is 1, so h prime of x is 1 when x is greater than 0. H prime of x is negative 1 when x is less than 0. And because it's a sharp point when x equals 0, h prime of x does not exist when x equals 0. So remember that our critical numbers is where f prime equals 0 or does not exist. Looking at our derivative, h prime of x, I see that it does not exist when x equals 0. So we can say our critical number is x equals 0 because f prime doesn't exist there. Number 3 is from an AP exam in the calculator section. So let's grab our calculator to do this problem. For f prime of x equal to cosine squared x over x minus 1/5, how many critical values does f have on the interval 0 to 10? So notice they're asking about the critical numbers of f, and they're already giving us f prime of x. How can we use our calculator to do this? Well, remember first of all that the critical number is where f prime equals 0 or does not exist. So if we go to our calculator, we want to examine the graph to find out where does f prime, which is this function, equal 0 or not exist. After we plug it into y equals, we can take a look at the window and adjust it so that it includes just this interval. So the x's go from 0 to 10, and because I only care about where this derivative function equals 0, I really have to just zoom in on the x-axis. So I've made my y min and y max negative 1 to 1 so that the x-axis is easier to see. Let's take a look at the graph. So I see this function, which is the derivative, is hitting 0 here, 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 and then never again. Let's make a quick sketch of that on our paper. So what did I see the graph do? It came down to cross the x-axis once, went back, crossed it a second time, came down, crossed it a third time, and then didn't cross it anymore. So if I'm looking for the critical numbers, which is where the derivative equals 0, I see one spot here, a second spot here, a third spot here. So there are 3 critical numbers or critical values for the function f. We don't necessarily have to see f because we're examining the derivative. So how did we examine the derivative? We plugged this in y equals all of this derivative function.